Welcome to Introduction to Geographic Information Systems. This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program. One of the defining features of GIS is their ability to combine spatially referenced data. A frequently occurring issue is the need to combine data from different sources that use different reference systems. This video looks at some of those issues. To combine two different datasets, you need to be able to know their locations. If geographic data is data relating to the Earth's surface, then to find a location you need to be able to accurately model that surface. Calculations of locations would be much easier if the world was a sphere and smooth. It would be simple geometry of angles and circumferences. Unfortunately, the Earth is neither. The Earth is actually an ellipsoid, not quite a sphere. The reason the Earth has a slightly ellipsoidal shape has to do with its rotation, which induces a centripetal force along the equator. This results in an equatorial axis that is roughly 21 kilometers longer than the polar axis. In other words, the Earth is a little fat in the middle and flatter on the top and bottom. Ellipsoid calculations aren't as easy as spherical calculations, but they're still well known and doable. However, the surface of the Earth is anything but uniform. The surface or topography of the land masses have large height variations between mountains and valleys. These variations make it impossible to approximate the shape of the Earth with any reasonably simple mathematical model. Thus, work has been undertaken to create reference surfaces to make calculation location easier. These reference surfaces are the geoid and, the unimaginatively named, ellipsoid. This has also led to the creation of geodesy, which is the science that provides the theoretical framework for this, and it studies the Earth's shape. Geodesy, through its different branches, provides methods and concepts that allow defining and using precise and rigorous coordinates to locate elements and phenomena that take place on Earth. The geoid is a reference for height, and ellipsoid is a reference for horizontal coordinates. So how does one go about creating a reference for height on the Earth when there are kilometers of difference in height across its surface? Imagine that the entire Earth's surface is covered by water. If we ignore tidal effects, the resultant water surface is a great reference point for height. It would be the same equal distance from the center everywhere as dictated by the pull of gravity. This is pretty close to what scientists have done, only using the oceans. Tide gauges have been used and then averaged over several years. The resulting water level represents an approximation to the geoid and is called the mean sea level. This gives the actual shape of the Earth. Now these measurements are done with satellites. Except, due to irregularities and mass anomalies in the core of the Earth, we actually have an undulated surface because gravitational pull is slightly varied in different locations around the world. This means the Earth's true shape is not perfectly smooth. So how are we to reconcile our need to work with a simple-ish mathematical model of the Earth's shape with the undulating nature of the Earth's surface? The solution is to align the geoid with the ellipsoid representation of the Earth and to map the Earth's surface features onto this ellipsoid. The alignment can be local, where the ellipsoid surface is closely fit to the geoid at a particular location, or geocentric, where the ellipsoid is aligned with the center of the Earth. How one chooses to align the ellipsoid to the geoid defines a datum. This is the point where the two are connected. There are hundreds of datums in use around the world. One of the most popular is the WGS84. However, the problem you will experience in GIS is that there are different versions of the ellipsoid, different measurements for the geoid, and different points where they meet. So if you combine data with different datums, you will end up with a misalignment. These are relatively small differences in a few hundred meters, but depending on your needs, this could have a big impact on your work. As such, when working with GIS, you need to check that your data is using the same datum. If not, convert them to all have the same datum. Once the issue of representing the Earth's shape is solved, you then have to think about how you reference locations on it. This is where a coordinate system comes in. Coordinate systems are frameworks that are used to define unique positions. For instance, in geometry we use x, horizontal, and y, vertical, coordinates to define points on a two-dimensional plane. The coordinate system that is most commonly used is latitude and longitude. There are hundreds of coordinate systems. Some are even local, so that you can have a coordinate system only for a country. Most of those tend to Cartesian coordinate systems. This is where two-dimensional coordinates, also known as planar rectangular coordinates, are used to describe the location of any point unambiguously. The 2D Cartesian coordinate system is a system of intersecting perpendicular lines, which contains two principal axes, called the x and y axis. The intersection of the x and y axis forms the origin. The plane is marked at intervals by equally spaced coordinate lines, called a map grid. It is important to know which coordinate systems is associated with a GIS file or a map document reference system. This is because coordinate systems will be tied to specific datums and as outlined above that can result in misaligned data. It is common when working with GIS to have layers in several different coordinate systems, or in the same coordinate system but using different parameters like a different datum. In order to be able to use those together, we have to work in a single coordinate system, and at least some of those layers will have to be converted to it. That is known as coordinate conversion. If the origin and destination coordinate systems have a different datum, coordinate conversion is called coordinate transformation. In a GIS, conversion and transformation capabilities thus allow to generate new layers that use a different coordinate system. To facilitate the use of coordinate reference systems, there are initiatives that organize and code them so each system can be easily identified by a unique code, called a spatial reference system identifier. The Earth being a spheroid presents other issues. A globe is a very common and very good representation of the three-dimensional, spheroid Earth. However, a GIS presents it as a flat surface. This means it is necessary to transform the three-dimensional shape of the Earth to a two-dimensional surface in order to obtain more useful map forms and map scales. To do that, you need to work with map projections. Map projections refer to the methods and procedures that are used to transform the spherical three-dimensional Earth into two-dimensional planar surfaces. Specifically, map projections are mathematical formulas that are used to translate latitude and longitude on the surface of the Earth to x and y coordinates on a plane. Since there are an infinite number of ways this translation can be performed, there are an infinite number of map projections. The mathematics behind map projections are beyond the scope of this video. For simplicity, the following discussion focuses on describing types of map projections, the distortions inherent to map projections, and the selection of appropriate map projections. Within the realm of maps and mapping, there are three surfaces used for map projections, i.e., surfaces on which we project the shadows of the graticule. These surfaces are the plane, the cylinder, and the cone. Planar projections. A planar projection, aka azimuthal projection, maps the Earth's surface features to a flat surface that touches the Earth's surface at a point, tangent case, or along a line of tangency, a secant case. This projection is often used in mapping polar regions but can be used for any location on the Earth's surface, in which case they are called oblique planar projections. A cylindrical map projection maps the Earth's surface onto a map rolled into a cylinder, which can then be flattened into a plane. The cylinder can touch the surface of the Earth along a single line of tangency, a tangent case, or along two lines of tangency, a secant case. The cylinder can be tangent to the equator or it can be oblique. A special case is the transverse aspect, which is tangent to lines of longitude. This is a popular projection used in defining the universal transverse Mercator coordinate systems. The UTM pieces covers the entire globe and is a popular coordinate system. It's important to note that the UTM pieces is broken down into zones and therefore limits its extent to these zones that are 6 degrees wide. For example, the state of Maine, USA, uses the UTM coordinate system, Zone 19 North, for most of its statewide GIS maps. Distortion is minimized along the tangent or secant lines and increases as the distance from these lines increases. Conical projection. A conical map projection maps the Earth's surface onto a map rolled into a cone. Like the cylindrical projection, the cone can touch the surface of the Earth along a single line of tangency, a tangent case, or along two lines of tangency, a secant case. Distortion is minimized along the tangent or secant lines and increases as the distance from these lines increases. Conical projections are also popular in European maps such as Europe-Albers equal area conic and Europe-Lambert conformal conic. To add to the complexity, we can situate each surface in any number of ways. For example, surfaces can focus on the equator or poles, or they can be oriented at any number of angles. In fact, naming conventions for many map projections include the surface as well as its orientation. For example, as the name suggests, planar projections use the plane, cylindrical projections use cylinders, and conic projections use the cone. For cylindrical projections, the standard aspect refers to when the cylinder is tangential to the equator, that is, the cylinder is oriented north to south. When the axis of the cylinder is oriented east-west, the aspect is called transverse, and all other orientations are referred to as oblique. The problem with projections is that when moving from the three-dimensional surface of the Earth to a two-dimensional plane, distortions are introduced. These are unavoidable and usually involve distance, angles, and areas. Depending on the purpose of the map, a series of trade-offs will need to be made with respect to such distortions. All projections distort real-world geographic features to some degree. The four spatial properties that are subject to distortion are shape, area, distance, and direction. Each map projection is good at preserving only one or two of the four spatial properties. So when working with small scale, i.e. large area maps, and when multiple spatial properties are to be preserved, it is best to break the analyses across different projections to minimize errors associated with spatial distortion. Map projections that accurately represent distances are referred to as equidistant projections. However, distances are only correct in one direction, usually running north to south, and are not correct everywhere across the map. Equidistant maps are frequently used for small-scale maps that cover large areas because they do a good job of preserving the shape of geographic features such as continents. Maps that represent angles or bearings between locations are called conformal. Conformal map projections are used for navigational purposes due to the importance of maintaining a bearing or heading when traveling great distances. The cost of preserving bearings is that areas tend to be quite distorted in conformal map projections. The Mercator projection is an example of a conformal projection and is famous for distorting Greenland. Equal area or equivalent projections preserve the quality of area. Such projections are of particular use when accurate measures or comparisons of geographical distributions are necessary. In an effort to maintain true proportions in the surface of the Earth, features sometimes become compressed or stretched depending on the orientation of the projection. Moreover, such projections distort distances as well as angular relationships. There are, theoretically, an infinite number of map projections to choose from. One of the key considerations behind the choice of map projection is to reduce the amount of distortion. The geographical object being mapped and the respective scale at which the map will be constructed are also important factors to think about. For instance, maps of the North and South Poles usually use planar or azimuthal projections, and conical projections are best suited for the middle latitude areas of the Earth. Features that stretch east-west, such as the country of Russia, are represented well with the standard cylindrical projection, while countries oriented north to south like Chile and the United Kingdom are better represented using a transverse projection. Within the scope of GIS, knowing and understanding map projections are critical. If they are not, geographical features will not be aligned properly, and any analyses performed will be inaccurate and incorrect. Most GIS include functions to assist in the identification of map projections, as well as to transform between projections in order to synchronize spatial data. Despite the capabilities of technology, an awareness of the potential and pitfalls that surround map projections is essential. I would like to take a second to mention geodesic geometries. Projected coordinate systems introduce errors in their geometric measurements because the distance between 2 points on a sphere or ellipsoid will be difficult to replicate on a projected coordinate system unless these points are relatively close to one another. In most cases, such errors can be tolerated if they are not great. However, if the scale of analysis is small, then the measurement errors associated with a projected coordinate system may no longer be acceptable. A way to circumvent projected coordinate system limitations is to adopt a geodesic solution. A geodesic distance is the shortest distance between 2 points on an ellipsoid, or spheroid. Likewise, a geodesic area measurement is one that is measured on an ellipsoid. Such measurements are independent of the underlying projected coordinate system. So if a geodesic measurement is more precise than a planar measurement, why not perform all spatial operations using geodesic geometry? In many cases, a geodesic approach to spatial operations can be perfectly acceptable and is even encouraged. The downside is in its computational requirements. It's far more computationally efficient to compute area/distance on a plane than it is on a spheroid. This is because geodesic calculations have no simple algebraic solutions, and this may be a computationally taxing approach of processing millions of segments. However, it may be in the future that this becomes standard in GIS and you have to worry less about projected coordinate systems introducing errors to your data. So in summary, differences in datum, coordinate system and projection can change the same locations between different layers in GIS. To be able to use different layers of data, you need to make sure you check these attributes.